Picture this, a massive asteroid, hurtling toward Earth at unimaginable speed, threatens to wipe out life as we know it. But before panic sets in, a network of powerful lasers stationed in orbit springs into action. In a matter of moments, the asteroid is vaporized, and humanity breathes a collective sigh of relief. This isn't science fiction. It's a glimpse into the future of space-based laser technology and its potential to revolutionize defense as we know it. Welcome to a world where the skies above hold the key to protecting life below. In this video, we'll explore 25 groundbreaking theories on how space-based lasers could be used for defense, from shielding Earth against cosmic threats to reshaping the way we think about warfare, communication, and even energy. These ideas aren't just futuristic dreams, they're possibilities grounded in cutting-edge science and technology, with the potential to transform not only how we defend ourselves but also how we live. So, buckle up and get ready to dive into a future where lasers in space are more than just tools, they're lifelines. By the end of this video, you'll see why space-based lasers could be one of the most important advancements of the 21st century. Let's begin. Now, let's zoom in on the first and perhaps most dramatic application of space-based lasers, asteroid defense. Imagine a scenario where a massive asteroid is detected on a collision course with Earth. The clock is ticking, and traditional methods like nuclear explosives or kinetic impactors might not be enough. This is where space-based lasers come into play. By positioning powerful laser systems in orbit, we could target the asteroid with precision, using a process called laser ablation. Here's how it works. The laser beam heats a small area of the asteroid's surface, causing it to vaporize and create a jet of gas. This gas acts like a tiny thruster, gently pushing the asteroid off its deadly trajectory. Over time, even a small nudge could be enough to steer it safely away from Earth. But the science doesn't stop there. Space-based lasers could also be used to break apart smaller asteroids entirely, reducing them to harmless fragments before they reach our atmosphere. This approach combines the principles of laser propulsion and energy delivery, showcasing how advanced technology can turn a catastrophic threat into a manageable challenge. And this isn't just theoretical. Real-world missions like NASA's Double Asteroid Redirection Test, or DART, have already demonstrated the potential of redirecting asteroids using kinetic impactors. Space-based lasers could take this concept even further, offering a faster, more precise, and less risky solution. By harnessing the power of light, we could one day have a planetary defense system that's not only effective but also scalable, capable of addressing threats of all sizes. So, while the idea of using lasers to stop asteroids might sound like something out of a sci-fi movie, the science behind it is very real, and it could be the key to safeguarding our planet from one of the universe's most unpredictable dangers. With that in mind, let's move on to the next theory, where we'll explore how space-based lasers could protect the satellites that keep our modern world connected. Now, shifting our focus from planetary defense to the skies above, let's explore how space-based lasers could play a crucial role in protecting the satellites that form the backbone of our modern world. Satellites are essential for everything from global communication and navigation to weather forecasting and national security. But they face constant threats, whether from natural hazards like space debris or deliberate attacks by adversaries. This is where space-based lasers could step in as a game-changing solution. Picture this, a piece of space debris hurtling toward a satellite at thousands of miles per hour. Even a tiny fragment could cause catastrophic damage, potentially disrupting vital services like GPS or internet connectivity. Space-based lasers could intercept and vaporize such debris before it becomes a threat. By focusing a high-energy laser beam on the debris, the intense heat would cause it to disintegrate into harmless particles, effectively clearing the path and safeguarding the satellite. This approach isn't just about defense, it's about ensuring the reliability of the systems we depend on every day, but the applications don't stop there. In a world where space is increasingly contested, satellites could also become targets in conflicts. Hostile nations or groups might attempt to disable or destroy critical satellites to gain a strategic advantage. Space-based lasers could act as a deterrent or a countermeasure, capable of disabling enemy satellites with precision. By targeting key components like solar panels or communication antennas, lasers could neutralize a threat without causing widespread destruction or creating additional debris. This precision is a major advantage over traditional methods, which often rely on kinetic impacts that can generate dangerous fragments. What makes this even more compelling is the scalability of the technology. A network of space-based lasers could monitor and protect multiple satellites simultaneously, creating a robust defense system for both civilian and military assets. This would not only enhance global security, but also pave the way for more ambitious space exploration and infrastructure projects, knowing that critical systems are shielded from harm. As we look to the future, the potential of space-based lasers to protect satellites is both exciting and essential. By addressing threats from debris and adversaries alike, this technology could ensure the continued operation of the systems that keep our world connected and secure. With that in mind, let's turn our attention to the next theory, where we'll dive into how space-based lasers could intercept ballistic missiles, offering a new layer of defense for our planet. Now, let's take a closer look at how space-based lasers could revolutionize missile defense, particularly during the critical boost phase of ballistic missiles. When a missile is launched, it goes through several stages, but the boost phase, the initial few minutes after liftoff, is when it's most vulnerable. This is because the missile is moving relatively slowly and its trajectory is predictable. Space-based lasers could capitalize on this window of opportunity to neutralize the threat before it becomes unstoppable. Imagine a scenario where a hostile nation launches a ballistic missile. From their position in orbit, space-based lasers could detect the launch almost instantly, thanks to their unobstructed view of the Earth's surface. Unlike ground-based systems, which are limited by the curvature of the Earth and atmospheric interference, space-based lasers have a clear line of sight to the missile from the moment it leaves the launch pad. This means they can respond much faster, delivering a precise laser beam to heat and disable the missile's propulsion system, causing it to fail before it reaches its target. One of the key advantages of space-based systems is their ability to cover vast areas. A single ground-based laser system is limited to defending a specific region, but a network of space-based lasers could provide global coverage. This would make it possible to intercept missiles launched from anywhere on the planet, offering a level of protection that ground-based systems simply can't match. Additionally, space-based lasers can operate continuously without being affected by weather conditions or the time of day, ensuring they're always ready to respond. Another significant benefit is the reduced risk of collateral damage. Traditional missile defense systems often rely on explosive interceptors, which can create debris and pose risks to nearby areas. Space-based lasers, on the other hand, use focused energy to disable missiles without causing explosions, minimizing the potential for unintended harm. This precision makes them not only more effective but also more ethical, as they reduce the risk to civilian populations and infrastructure. As we consider the future of missile defense, it's clear that space-based lasers could offer a game-changing solution. By intercepting threats during their most vulnerable phase, providing global coverage and minimizing collateral damage, this technology could redefine how we protect our planet from ballistic missile attacks. With that in mind, let's move forward to explore another fascinating application of space-based lasers, their potential role in space warfare and the ethical questions that come with it. Now, shifting our focus to the realm of space warfare, let's explore how space-based lasers could play a pivotal role in future conflicts beyond Earth's atmosphere. In this high-stakes environment, the ability to neutralize enemy spacecraft or space stations could become a critical factor in maintaining strategic dominance. Space-based lasers, with their precision and speed, offer a unique advantage in this domain. Picture a scenario where two nations are engaged in a conflict that extends into space. Enemy satellites crucial for communication, navigation, or surveillance could be targeted by space-based lasers. These lasers could deliver concentrated beams of energy to disable or destroy these assets, effectively blinding or crippling the adversary's operations. Unlike traditional kinetic weapons, which rely on physical projectiles, lasers can strike almost instantaneously, making them nearly impossible to evade once targeted. Space stations, too, could become vulnerable to such systems. A hostile nation could deploy space-based lasers to disrupt or destroy an opponent's orbital habitat, cutting off their access to critical resources or research capabilities. The ability to project power in this way could shift the balance of power in space, making it a new frontier for military strategy. However, the use of space-based lasers in warfare raises significant ethical questions. Militarizing space could lead to an arms race, with nations rushing to develop and deploy increasingly advanced weapons systems. This could destabilize international relations and increase the risk of conflict, not just in space but on Earth as well. The Outer Space Treaty of 1967, which prohibits the placement of weapons of mass destruction in space, was a step toward preventing such scenarios. But as technology advances, the lines between defensive and offensive capabilities blur, challenging the existing framework of space governance. Another concern is the potential for unintended consequences. Destroying satellites or space stations could create vast amounts of space debris, posing risks to all spacefaring nations. This debris could collide with other satellites or spacecraft, creating a cascade of collisions known as the Kessler syndrome, which could render entire orbits unusable for decades. As we consider the implications of space-based lasers in warfare, it's clear that this technology holds both promise and peril. While it offers a powerful tool for defense and strategic advantage, it also introduces complex ethical and practical challenges. Balancing the benefits of such systems with the need to preserve the peaceful use of space will be crucial as we move forward. With that in mind, let's turn our attention to another intriguing application of space-based lasers: their potential role in planetary defense and how they could safeguard future colonies on worlds like Mars. Now, let's venture beyond Earth and consider how space-based lasers could play a vital role in protecting other planets, particularly Mars, as humanity takes its first steps toward becoming a multi-planetary species. Imagine a future where colonies on Mars are thriving, but they face constant threats from micrometeoroids and intense solar radiation. Space-based lasers could serve as a first line of defense, ensuring the safety and sustainability of these off-world settlements. Micrometeoroids, tiny but fast-moving particles, pose a significant risk to both spacecraft and planetary habitats. A single impact could breach a colony's protective shielding or damage critical infrastructure. Space-based lasers could detect and neutralize these threats by vaporizing incoming micrometeoroids before they reach the surface. This capability would not only protect human lives, but also safeguard the expensive equipment and resources needed for survival on Mars. Solar radiation is another major challenge for Martian colonies. Unlike Earth, Mars lacks a strong magnetic field and thick atmosphere to shield its surface from harmful solar particles and cosmic rays. Prolonged exposure to this radiation could endanger astronauts and compromise long-term colonization efforts. Space-based lasers could be deployed to create artificial shields, deflecting or diffusing harmful radiation before it reaches the planet's surface. This innovative use of laser technology could make Mars a safer and more viable destination for future explorers. Beyond protection, space-based lasers could also support colonization efforts in other ways. For instance, they could assist in mining operations by precisely cutting through Martian rock or ice, enabling the extraction of essential resources like water and minerals. Additionally, lasers could be used to clear landing zones for spacecraft, ensuring safe and efficient arrivals and departures from the Martian surface. The integration of space-based lasers into planetary defense systems would mark a significant leap forward in our ability to explore and inhabit other worlds. By addressing the unique challenges of space environments, these lasers could pave the way for sustainable colonies on Mars and beyond. As we continue to push the boundaries of human exploration, the role of advanced technologies like space-based lasers will become increasingly critical. Next, we'll explore how these lasers could tackle another pressing issue, the growing problem of space debris and their potential to clean up Earth's orbit. Now, let's shift our focus to a pressing issue closer to home, the growing problem of space debris. As humanity continues to launch satellites, spacecraft, and other objects into orbit, Earth's surroundings are becoming increasingly cluttered with defunct equipment, spent rocket stages, and fragments from collisions. This space junk poses a serious threat to active satellites, the International Space Station, and future space missions. Enter space-based lasers, a potential game-changer in tackling this orbital hazard. Space debris, ranging from tiny screws to large satellite remnants, travels at incredible speeds, often exceeding 17,000 miles per hour. At such velocities, even a small piece of debris can cause catastrophic damage to spacecraft or satellites. The risk of collisions is rising as the amount of debris continues to grow, creating a dangerous environment for both current and future space operations. Space-based lasers could offer a sustainable solution by either vaporizing smaller debris or redirecting larger pieces into safer orbits or toward Earth's atmosphere, where they would burn up harmlessly. The concept of using lasers for debris cleanup is both innovative and practical. For smaller debris, high-powered lasers could focus intense beams of energy to heat and vaporize the objects, effectively eliminating them. For larger debris, lasers could be used to nudge the objects into new trajectories, either pushing them into a graveyard orbit or guiding them toward atmospheric re-entry. This approach would not only reduce the risk of collisions but also help prevent the cascading effect known as the Kessler syndrome, where one collision generates more debris, leading to a chain reaction of further collisions. One of the key advantages of space-based lasers in debris cleanup is their precision. Unlike ground-based systems, which face challenges like atmospheric interference, space-based lasers can operate with greater accuracy and efficiency. They could be deployed in strategic orbits, forming a network capable of monitoring and addressing debris in real time. This proactive approach would ensure the long-term sustainability of Earth's orbital environment, safeguarding critical infrastructure like communication satellites, weather monitoring systems, and navigation networks. The potential benefits of space-based lasers for debris cleanup extend beyond safety. By maintaining a cleaner orbital environment, we can reduce the costs associated with satellite shielding, collision avoidance maneuvers, and mission planning. This, in turn, could lower the barriers to entry for new space ventures, fostering innovation and exploration. Moreover, a debris-free orbit would enhance the reliability of global services that depend on satellites, from internet connectivity to disaster response. As we look to the future, the role of space-based lasers in addressing the space debris problem cannot be overstated. They represent a forward-thinking solution to a challenge that grows more urgent with each passing year. By leveraging this technology, we can ensure that Earth's orbit remains a safe and accessible frontier for generations to come. Next, we'll delve into another critical application of space-based lasers, their potential role in anti-satellite warfare and the strategic implications of such systems. Now, let's turn our attention to a more contentious application of space-based lasers, their potential role in anti-satellite warfare. In an era where satellites are critical to communication, navigation, and surveillance, the ability to disable or destroy an adversary's satellites could provide a significant strategic advantage. Space-based lasers, with their precision and speed, could become a key tool in this high-stakes domain. Imagine a scenario where tensions escalate between nations, and the ability to disrupt an enemy's satellite network could tilt the balance of power. Space-based lasers could target and disable satellites by focusing intense beams of energy on their sensitive components, such as solar panels or communication antennas. This would render the satellites inoperable without the need for explosive force, minimizing the creation of additional space debris, a critical consideration given the growing problem of orbital clutter. One of the most significant advantages of using space-based lasers in anti-satellite warfare is their ability to act swiftly and with precision. Unlike traditional kinetic weapons, which rely on physical impact, lasers can deliver energy almost instantaneously over vast distances. This means that a single laser system could potentially neutralize multiple targets in quick succession, providing a decisive edge in a conflict. Additionally, space-based lasers are less vulnerable to countermeasures compared to ground-based systems, as they operate outside the reach of most terrestrial defenses. However, the use of space-based lasers in this capacity raises serious ethical and strategic concerns. Disabling or destroying satellites could have far-reaching consequences, not only for the targeted nation but also for the global community. Many satellites serve dual purposes, supporting both military and civilian functions. For example, disrupting a satellite used for weather forecasting could hinder disaster response efforts, while targeting navigation satellites could disrupt global transportation systems. The potential for collateral damage is significant, and the international community would likely view such actions as highly provocative. Moreover, the deployment of space-based lasers for anti-satellite warfare could trigger an arms race in space, leading to increased militarization and instability. Nations might feel compelled to develop their own space-based weapons to counter potential threats, creating a cycle of escalation. This could undermine decades of efforts to preserve space as a peaceful domain for exploration and cooperation. The Outer Space Treaty of 1967, which prohibits the placement of weapons of mass destruction in space, does not explicitly ban conventional weapons like lasers, leaving room for interpretation and potential exploitation. Despite these challenges, the strategic value of space-based lasers in anti-satellite warfare cannot be ignored. They offer a means of neutralizing critical enemy assets without the destructive fallout of kinetic strikes, making them a potentially attractive option for military planners. However, their use would require careful consideration of the broader implications, including the risk of escalating conflicts and the impact on global stability. As we consider the role of space-based lasers in anti-satellite warfare, it's clear that this technology represents both a powerful tool and a significant ethical dilemma. Balancing the strategic advantages with the potential consequences will be crucial as nations navigate the complexities of modern warfare. Next, we'll explore another fascinating application of space-based lasers, their potential as directed energy weapons and how they compare to traditional kinetic systems. Now, shifting our focus to a broader yet equally fascinating application, let's explore the concept of directed energy weapons and how space-based lasers fit into this cutting-edge category. Directed energy weapons, as the name suggests, use focused energy, such as lasers, microwaves, or particle beams, to target and neutralize threats. Unlike traditional kinetic weapons, which rely on physical projectiles to cause damage, directed energy weapons harness the power of light or electromagnetic waves to achieve their effects. Space-based lasers, with their ability to operate in the vacuum of space and deliver energy at the speed of light, represent a revolutionary step forward in this field. One of the most compelling advantages of directed energy weapons, particularly space-based lasers, is their unparalleled precision. Traditional kinetic weapons, such as missiles or bullets, depend on explosive force to destroy targets, which often results in unintended collateral damage. In contrast, space-based lasers can be finely tuned to focus their energy on specific components of a target, such as a missile's guidance system or a satellite's solar panels. This precision not only increases the effectiveness of the weapon, but also minimizes the risk of harming nearby structures, civilians, or other assets. For example, a space-based laser could disable an incoming missile without causing an explosion that might endanger nearby aircraft or populated areas. Another key benefit of space-based lasers as directed energy weapons is their reduced reliance on physical ammunition. Traditional kinetic weapons require a constant supply of bullets, missiles, or other projectiles, which can be costly to produce, store, and transport. Space-based lasers, on the other hand, draw their power from energy sources like solar panels or nuclear reactors, allowing them to operate for extended periods without the need for resupply. This makes them a more sustainable and cost-effective option in the long run, especially for missions that require continuous defense capabilities. However, it's important to note that directed energy weapons are not without their challenges. One of the primary limitations of space-based lasers is their dependence on line-of-sight targeting. Unlike kinetic weapons, which can follow a curved trajectory to reach their targets, lasers travel in straight lines. This means that space-based lasers must have a clear, unobstructed path to their targets, which can be complicated by factors like orbital mechanics or the curvature of the Earth. Additionally, the effectiveness of lasers can be diminished by atmospheric interference, though this is less of a concern in the vacuum of space. When comparing space-based lasers to traditional kinetic weapons, it's clear that each has its own strengths and weaknesses. Kinetic weapons are well suited for scenarios where brute force is required, such as destroying heavily armored targets or creating large-scale damage. Directed energy weapons, on the other hand, excel in situations that demand precision and minimal collateral damage, such as disabling enemy satellites or intercepting missiles. The choice between these two types of weapons often depends on the specific objectives of a mission and the nature of the threat being addressed. As we look to the future, the potential of space-based lasers as directed energy weapons is both exciting and complex. Their ability to deliver precise, energy-based strikes could revolutionize the way we approach defense and warfare, offering new possibilities for protecting assets in space and on Earth. However, their development and deployment will require careful consideration of technical, ethical, and strategic factors. Next, we'll delve into how space-based lasers could enhance surveillance systems, providing real-time data on threats from above. Now, let's turn our attention to how space-based lasers could revolutionize surveillance systems, offering unprecedented capabilities for monitoring threats both on Earth and in space. Imagine a network of satellites equipped with advanced laser technology, working in tandem with artificial intelligence to provide real-time data on potential dangers. This integration could transform the way we detect, track, and respond to threats, making surveillance faster, more accurate, and far more efficient. One of the most significant advantages of using lasers in space-based surveillance is their ability to deliver high-resolution data at incredible speeds. Traditional surveillance systems often rely on cameras or radar, which can be limited by factors like weather conditions or the need for large amounts of power. Lasers, on the other hand, can transmit precise information over vast distances without being hindered by atmospheric interference. For example, a laser-equipped satellite could scan a specific area of the Earth's surface, capturing detailed images of military installations, natural disasters, or even illegal activities like deforestation or poaching. This data could then be relayed to ground stations in real time, enabling rapid decision-making and response. The integration of lasers with artificial intelligence further enhances their potential for surveillance. AI algorithms can analyze the vast amounts of data collected by laser systems, identifying patterns or anomalies that might indicate a threat. For instance, an AI-powered surveillance network could detect the launch of a missile, track its trajectory, and predict its target, all within seconds. This level of speed and accuracy would be nearly impossible to achieve with traditional methods, giving defense systems a critical edge in preventing attacks or mitigating damage. Another exciting application of space-based laser surveillance is the ability to monitor space itself. As humanity becomes more reliant on satellites for communication, navigation, and scientific research, the need to protect these assets from threats like space debris or hostile actions becomes increasingly urgent. Lasers could be used to track and identify objects in orbit, distinguishing between harmless debris and potential threats. In some cases, they could even be employed to neutralize dangerous objects by vaporizing them or altering their trajectory, ensuring the safety of vital space infrastructure. The synergy between lasers, AI, and satellite networks also opens up possibilities for global collaboration. Imagine a system where multiple countries contribute to a shared surveillance network, pooling resources and data to enhance global security. This kind of cooperation could lead to more effective monitoring of international borders, early warning systems for natural disasters, and even the prevention of conflicts by providing transparent, real-time information to all parties involved. Of course, the development of such advanced surveillance systems is not without its challenges. Issues like data privacy, the potential for misuse, and the technical complexities of integrating lasers with AI and satellite networks must be carefully addressed. However, the potential benefits ranging from enhanced national security to improved disaster response make this an area of research worth pursuing. As we continue to explore the possibilities of space-based lasers, it's clear that their role in surveillance could be transformative. By combining cutting-edge technology with innovative strategies, we could create a safer, more connected world. Next, we'll dive into how lasers could revolutionize communication in space, offering faster, more secure ways to transmit information across vast distances. Now, let's shift our focus to a groundbreaking application of space-based lasers, communication. Imagine a future where data travels across the cosmos at the speed of light, enabling instant, secure, and crystal-clear communication between satellites, spacecraft, and Earth. This is the promise of laser-based communication systems, a technology that could revolutionize how we transmit information in space. Traditional communication systems in space rely heavily on radio waves, which, while reliable, have significant limitations. Radio waves are slower compared to light, and their bandwidth is limited, meaning they can only carry so much data at once. This becomes a bottleneck as our reliance on satellites grows, especially for applications like global internet coverage, scientific research, and deep space exploration. Enter space-based lasers, which use light to transmit data. Because light travels faster and can carry more information, laser communication offers a dramatic upgrade in speed and capacity. For example, a laser system could transmit high-definition video or massive datasets in seconds, something that would take minutes or even hours with radio waves. One of the most compelling advantages of laser communication is its security. Unlike radio waves, which spread out and can be intercepted over long distances, laser beams are highly focused and difficult to detect or disrupt. This makes them ideal for transmitting sensitive information, such as military communications or confidential scientific data. Imagine a scenario where a spacecraft on a mission to Mars sends critical data back to Earth. With laser communication, that data could be transmitted securely and without interference, ensuring that it reaches its destination intact. Another key benefit is the ability to maintain high-speed communication over vast distances. As we venture further into space, the delay in communication becomes a significant challenge. For instance, sending a signal from Mars to Earth using radio waves can take anywhere from 4 to 24 minutes, depending on the planet's positions. Laser communication could reduce this delay, enabling near-instantaneous data transfer. This would be a game-changer for missions to distant planets or even interstellar travel, where real-time communication is essential for navigation and decision-making. The integration of laser communication with existing satellite networks also opens up exciting possibilities. Satellites equipped with laser systems could form a high-speed interplanetary internet, connecting spacecraft, space stations, and ground-based facilities seamlessly. This network could support everything from scientific research to commercial ventures, such as asteroid mining or space tourism. For example, a mining operation on the Moon could use laser communication to send real-time updates to Earth, allowing operators to monitor progress and make adjustments instantly. Of course, implementing laser communication systems is not without challenges. Precise alignment is required to ensure that the laser beams reach their intended targets, and atmospheric interference can disrupt signals when communicating with Earth. However, advancements in adaptive optics and AI-driven tracking systems are helping to overcome these hurdles, making laser communication increasingly viable. As we look to the future, it's clear that space-based laser communication has the potential to transform how we connect across the cosmos. By offering faster speeds, greater security, and the ability to bridge vast distances, this technology could become the backbone of our interplanetary communication infrastructure. Next, we'll explore how lasers could be used to beam power from space to Earth, unlocking new possibilities for energy distribution. Now, let's turn our attention to another fascinating application of space-based lasers, power beaming. Picture a world where energy is harvested directly from space and transmitted to Earth or other spacecraft using laser technology. This concept, known as space-based power beaming, could fundamentally change how we generate and distribute energy, offering a sustainable solution to some of our planet's most pressing challenges. At the heart of this idea is space-based solar power. Unlike traditional solar panels on Earth, which are limited by weather, nighttime, and atmospheric interference, solar panels in space can capture sunlight continuously without interruption. These panels would collect solar energy and convert it into electricity, which could then be transmitted to Earth or other locations using highly focused laser beams. This process, known as power beaming, involves converting electrical energy into laser light, sending it across vast distances, and then converting it back into electricity upon arrival. One of the most significant advantages of space-based power beaming is its potential to provide a constant, reliable energy source. On Earth, solar and wind energy are intermittent, dependent on weather conditions and time of day. But in space, solar panels can operate 24 hours a day, 7 days a week, capturing energy that could be beamed to any location on the planet. This could revolutionize energy distribution, especially in remote or disaster-stricken areas where traditional power grids are unavailable or damaged. Another exciting possibility is the use of power beaming for space exploration. Imagine a spacecraft equipped with a receiver that could harvest energy from a space-based laser system. This would eliminate the need for heavy, bulky fuel tanks, allowing spacecraft to travel farther and faster. For example, a mission to Mars could rely on power beaming to provide continuous energy for propulsion, life support, and scientific instruments, significantly reducing the risks and costs associated with long-duration space travel. The environmental benefits of space-based power beaming are also worth noting. By reducing our reliance on fossil fuels, this technology could help mitigate climate change and decrease air pollution. Additionally, because the energy is transmitted wirelessly, there would be no need for extensive infrastructure like power lines or pipelines, minimizing the impact on natural landscapes and ecosystems. However, there are challenges to overcome. Transmitting energy over such vast distances requires precise alignment and efficient conversion processes to minimize energy loss. Atmospheric conditions such as clouds or storms can also interfere with the laser beams, potentially disrupting the energy transfer. Researchers are actively working on solutions, including advanced tracking systems and adaptive optics, to address these issues and make power beaming a practical reality. As we look to the future, space-based power beaming holds immense promise. By harnessing the limitless energy of the sun and transmitting it across the cosmos, this technology could provide a clean, sustainable energy source for Earth and beyond. Next, we'll explore how space-based lasers could play a crucial role in counter-space operations, shaping the future of global security. Now, shifting our focus to the realm of defense, let's explore how space-based lasers could redefine counter-space operations. In an era where space has become a critical domain for military and civilian infrastructure, the ability to control or neutralize enemy assets in orbit could determine the balance of power on Earth. Space-based lasers offer a unique and precise tool for disrupting or disabling hostile satellites, communication networks, and other space-based systems that adversaries rely on. Imagine a scenario where an enemy spy satellite is gathering sensitive information or a communication satellite is coordinating military operations. Space-based lasers could be deployed to target and disable these assets with pinpoint accuracy. By focusing a high-energy laser beam on a satellite's solar panels, sensors, or communication antennas, the system could render it inoperable without the need for physical destruction. This approach minimizes the risk of creating space debris, which is a growing concern in orbital environments. The strategic importance of controlling space cannot be overstated. Satellites play a vital role in modern warfare, providing everything from real-time intelligence and navigation to secure communication and early warning systems. By developing the capability to disrupt or disable enemy satellites, a nation could gain a significant advantage in both conventional and asymmetric conflicts. For example, disabling an adversary's communication satellites could cripple their ability to coordinate troops or relay orders, while targeting reconnaissance satellites could blind their intelligence-gathering capabilities. One of the key advantages of using space-based lasers for counter-space operations is their speed and precision. Unlike ground-based systems, which may face delays due to atmospheric interference or the need to launch interceptors, space-based lasers can act almost instantaneously. Positioned in orbit, these systems can target satellites across vast distances, providing a rapid response to emerging threats. Additionally, their precision reduces the risk of collateral damage, ensuring that only the intended target is affected. However, the use of space-based lasers in counter-space operations raises important ethical and legal questions. The militarization of space is a contentious issue, with many nations advocating for the peaceful use of outer space under international treaties. Deploying weapons in orbit could escalate tensions and trigger an arms race, potentially destabilizing global security. Balancing the need for defense with the principles of space diplomacy will be a critical challenge as this technology evolves. Looking ahead, the development of space-based lasers for counter-space operations could reshape the future of warfare and global security. By providing a means to control the space domain, these systems offer a powerful tool for deterrence and defense. Next, we'll delve into the concept of space-based laser shields, exploring how they could protect spacecraft and Earth from a variety of threats. Now, let's turn our attention to an innovative concept that could revolutionize space and planetary defense: space-based laser shields. Picture this: a protective barrier of laser beams deployed in orbit, capable of shielding spacecraft, satellites, or even Earth itself from a variety of threats. Whether it's harmful radiation, micrometeoroids, or even directed energy attacks, these laser shields could serve as a futuristic line of defense, safeguarding critical assets and infrastructure. The idea of a laser shield might sound like science fiction, but the principles behind it are rooted in real-world physics. For instance, lasers could be used to vaporize micrometeoroids before they collide with spacecraft, preventing damage to sensitive equipment. Similarly, a network of lasers could deflect or neutralize harmful radiation, such as solar flares or cosmic rays, which pose significant risks to both astronauts and electronics in space. By creating a dynamic shield that adapts to incoming threats, space-based lasers could offer unparalleled protection in the harsh environment of space. One of the most intriguing applications of laser shields is their potential to defend against directed energy attacks. In a future where space-based weapons become a reality, having a countermeasure like a laser shield could be crucial. These shields could detect and intercept incoming laser beams, either by deflecting them or absorbing their energy. This dual-purpose capability defending against natural and man-made threats makes laser shields a versatile tool for space security. However, the development of such systems comes with significant challenges. Creating a laser shield that can operate effectively over vast distances requires immense power and precision. The energy demands alone are staggering, as generating and sustaining high-energy laser beams for extended periods would necessitate advanced power sources, such as space-based solar arrays or nuclear reactors. Additionally, the technology needed to detect and respond to threats in real time is still in its infancy, requiring breakthroughs in sensors, artificial intelligence, and laser targeting systems. Another hurdle is the sheer scale of deployment. Protecting an entire spacecraft or a region of Earth would require a network of lasers working in perfect harmony. Coordinating these systems to respond to multiple threats simultaneously adds another layer of complexity. Moreover, the cost of developing, launching, and maintaining such a network would be astronomical, raising questions about its economic feasibility. Despite these challenges, the potential benefits of space-based laser shields are too significant to ignore. For future missions to Mars or beyond, protecting astronauts and equipment from radiation and micrometeoroids could be the difference between success and failure. On Earth, such shields could defend against solar storms that threaten power grids and communication networks, potentially saving billions in damages. As we look to the future, the concept of space-based laser shields opens up exciting possibilities for both defense and exploration. While the road to implementation is fraught with technical and financial obstacles, the promise of a safer, more secure space environment makes this a goal worth pursuing. Next, we'll dive into the world of space-based laser drones, exploring how these autonomous systems could take on a variety of defense tasks in orbit. Now, shifting our focus to a more agile and versatile application of space-based lasers, let's explore the concept of space-based laser drones. Imagine a fleet of compact, autonomous drones equipped with precision laser systems patrolling the vast expanse of space. These drones could perform a wide range of defense tasks, from reconnaissance missions to targeted strikes, all while operating independently or as part of a coordinated network. One of the most compelling advantages of space-based laser drones is their ability to adapt to various scenarios. For instance, they could be deployed to monitor and gather intelligence on potential threats, such as suspicious satellites or space debris. Equipped with advanced sensors and cameras, these drones could provide real-time data, enabling swift decision-making and response. In situations where immediate action is required, the same drones could transition from reconnaissance to defense, using their laser systems to neutralize threats with pinpoint accuracy. The autonomy of these drones is another game-changing feature. Powered by artificial intelligence, they could operate without constant human intervention, making split-second decisions based on pre-programmed protocols or real-time analysis. This level of independence is crucial in the unpredictable environment of space, where delays in communication with Earth could mean the difference between success and failure. By combining AI with laser technology, these drones could become highly efficient guardians of space assets, capable of identifying and addressing threats faster than ever before. But the potential of space-based laser drones doesn't stop at defense. They could also play a vital role in maintaining the safety and functionality of space infrastructure. For example, they could be tasked with inspecting and repairing satellites, ensuring their longevity and performance. In more extreme cases, they could even dismantle or deorbit defunct satellites, helping to mitigate the growing problem of space debris. This dual-purpose capability, defense and maintenance, makes laser drones an invaluable tool for the future of space operations. Of course, developing and deploying these drones comes with its own set of challenges. Ensuring their reliability in the harsh conditions of space, where extreme temperatures and radiation are constant threats, requires cutting-edge engineering. Additionally, the integration of AI and laser systems demands significant advancements in both fields, as well as rigorous testing to guarantee their effectiveness and safety. The cost of producing and launching these drones is another consideration, though their potential benefits may outweigh the investment. As we look ahead, the possibilities for space-based laser drones are both exciting and transformative. From safeguarding critical satellites to conducting precision strikes against threats, these autonomous systems could redefine how we approach space defense. Their ability to operate independently, adapt to changing conditions, and perform multiple roles makes them a cornerstone of future space security strategies. Next, we'll examine the concept of space-based laser arrays, exploring how large networks of lasers could work together to address even more complex challenges. Now, let's take a step further into the realm of space-based defense and explore the concept of space-based laser arrays. Picture this: a vast network of lasers, strategically positioned in orbit, working in unison to create a formidable shield against a variety of threats. Unlike single laser systems, these arrays would operate as a coordinated unit, capable of addressing multiple challenges at once, from incoming missiles to swarms of space debris. The idea behind space-based laser arrays is to amplify the effectiveness of laser technology by combining the power of multiple systems. Imagine a scenario where a single laser might struggle to neutralize a large or fast-moving target. With an array, several lasers could focus their energy on the same threat, increasing the likelihood of a successful interception. Alternatively, the array could divide its attention, with different lasers targeting separate threats simultaneously. This flexibility makes laser arrays a highly versatile solution for space defense. One of the most significant advantages of these arrays is their ability to cover a wide area. By distributing lasers across different orbital positions, they could monitor and protect vast regions of space, ensuring comprehensive coverage. For example, an array could be designed to safeguard critical satellites in geostationary orbit, where communication and weather satellites are often located. At the same time, it could extend its reach to lower orbits, where threats like space debris are more prevalent. This multi-layered defense system would provide a robust shield for both current and future space infrastructure. Another key feature of laser arrays is their scalability. As new threats emerge or technology advances, additional lasers could be added to the network, enhancing its capabilities without requiring a complete overhaul. This modular approach allows for continuous improvement and adaptation, ensuring that the defense system remains effective in the face of evolving challenges. Moreover, the integration of artificial intelligence could enable the array to autonomously prioritize threats, allocate resources, and optimize its performance in real time. However, deploying such a system is not without its hurdles. The sheer scale of a laser array would require significant investment in terms of both technology and infrastructure. Launching and maintaining multiple lasers in orbit would demand advanced engineering and reliable power sources, such as solar energy or nuclear power. Additionally, coordinating the array's operations would necessitate sophisticated communication and control systems capable of handling the complexities of space-based defense. Despite these challenges, the potential benefits of space-based laser arrays are immense. By creating a network of interconnected lasers, we could establish a proactive and adaptable defense system capable of addressing a wide range of threats with precision and efficiency. This approach not only enhances our ability to protect space assets, but also paves the way for more ambitious endeavors, such as safeguarding future lunar or Martian colonies. As we continue to push the boundaries of space technology, the concept of laser arrays offers a glimpse into a future where space-based defense is both comprehensive and dynamic. Next, we'll delve into the fascinating idea of using lasers for propulsion, exploring how this technology could revolutionize space travel and exploration. Now, shifting our focus to a groundbreaking application of space-based lasers, let's explore how this technology could revolutionize propulsion systems for spacecraft and satellites. Imagine a future where lasers are not just tools for defense or communication, but also the driving force behind faster, more efficient space travel. This is the promise of space-based laser propulsion, a concept that could redefine how we navigate the cosmos. At its core, laser propulsion works by using powerful beams of light to push or pull objects through space. Unlike traditional rocket engines that rely on chemical reactions to generate thrust, laser propulsion harnesses the energy of light to propel spacecraft. Here's how it could work. A ground-based or space-based laser system would direct a concentrated beam of light at a spacecraft equipped with a reflective sail. The photons in the laser beam would transfer their momentum to the sail, creating thrust and accelerating the spacecraft to incredible speeds. This method could enable spacecraft to reach velocities far beyond what conventional rockets can achieve, drastically reducing travel times within our solar system and beyond. One of the most exciting possibilities of laser propulsion is its potential for interstellar missions. Current propulsion technologies make journeys to even the nearest stars, like Proxima Centauri, prohibitively long, taking tens of thousands of years. With laser propulsion, however, we could theoretically send probes to nearby star systems in just a few decades. For instance, projects like Breakthrough Starshot aim to use powerful laser arrays to propel tiny, lightweight probes to a significant fraction of the speed of light, making interstellar exploration a tangible reality within our lifetimes. But the benefits of laser propulsion aren't limited to interstellar travel. Closer to home, this technology could revolutionize how we maneuver satellites and spacecraft in Earth's orbit. Traditional methods of adjusting a satellite's position often require carrying large amounts of fuel, which adds weight and limits mission flexibility. With laser propulsion, satellites could be repositioned or maintained in orbit using external laser beams, eliminating the need for onboard fuel and extending their operational lifespans. This could lead to more sustainable and cost-effective space operations, from maintaining communication networks to monitoring Earth's climate. Of course, developing laser propulsion systems comes with its own set of challenges. The technology requires extremely precise targeting and control to ensure the laser beam remains focused on the spacecraft's sail over vast distances. Additionally, the materials used for the reflective sails must be lightweight yet durable enough to withstand the intense energy of the laser beam. Overcoming these hurdles will require significant advancements in materials science, laser technology, and space engineering. Despite these challenges, the potential of space-based laser propulsion is too compelling to ignore. By enabling faster travel, more efficient orbital adjustments, and even interstellar exploration, this technology could open up new frontiers in space exploration and utilization. As we continue to push the boundaries of what's possible, laser propulsion stands as a testament to the innovative spirit driving humanity's journey into the stars. Next, we'll turn our attention to another fascinating application of space-based lasers: countermeasures. How can lasers be used to defend against enemy laser systems, and what does this mean for the future of space defense? Stay tuned as we dive into this intriguing topic. Now, let's pivot to a critical aspect of space-based laser technology: countermeasures. In a future where lasers play a central role in defense, the ability to defend against enemy laser systems becomes just as important as deploying them. Space-based laser countermeasures could serve as a vital line of defense, ensuring that our assets remain protected in an increasingly contested space environment. One of the primary ways lasers can counter enemy systems is by deflecting or absorbing incoming laser beams. Imagine a scenario where an adversary directs a high-energy laser at a satellite or spacecraft. A countermeasure system could deploy reflective surfaces or specialized coatings designed to scatter or absorb the incoming energy, rendering the attack ineffective. This approach relies on advanced materials engineered to withstand extreme heat and energy levels, ensuring that critical systems remain operational even under direct laser fire. The development of laser-resistant materials is a key area of research in this field. Scientists are exploring innovative solutions such as ultra-reflective coatings, heat-dissipating composites, and adaptive materials that can change their properties in response to laser exposure. For example, some materials are designed to reflect specific wavelengths of light, while others can absorb and redistribute energy to prevent damage. These advancements could pave the way for spacecraft and satellites equipped with built-in defenses against laser attacks, significantly enhancing their survivability in hostile environments. Another intriguing possibility is the use of active countermeasures, where space-based lasers themselves are employed to neutralize incoming threats. In this scenario, a defensive laser system could detect and track an enemy laser beam, then fire a counter beam to disrupt or cancel out the incoming energy. This method would require highly precise targeting and real-time coordination, but it could offer a dynamic and effective way to protect assets from laser-based attacks. The strategic implications of space-based laser countermeasures are profound. By developing robust defenses against laser threats, nations could deter potential adversaries and maintain the integrity of their space infrastructure. This balance between offense and defense will be crucial as space becomes an increasingly contested domain, with lasers playing a dual role as both weapons and shields. As we look to the future, the development of laser countermeasures and resistant materials will be essential for ensuring the safety and sustainability of space operations. These technologies not only protect our assets but also contribute to a more stable and secure space environment, where exploration and innovation can thrive without the constant threat of conflict. Next, we'll explore another fascinating application of space-based lasers: weather control. Could lasers one day be used to manipulate Earth's weather patterns, and what would that mean for both defense and civilian life? Stay tuned as we uncover the possibilities. Now, let's shift our focus to a concept that sounds like it's straight out of science fiction but could one day become a reality: space-based laser weather control. The idea of using lasers to manipulate Earth's weather patterns is both fascinating and controversial, raising questions about the potential benefits and risks of such technology. At its core, this theory explores how high-powered lasers could be used to influence weather systems. For instance, lasers might be deployed to disperse severe storms, such as hurricanes or typhoons, by targeting and disrupting their formation. By heating specific areas of the atmosphere, lasers could potentially weaken storm systems, reducing their intensity and minimizing the damage they cause. This application could be a game-changer for disaster prevention, saving lives and protecting infrastructure in vulnerable regions. Another possibility is the creation of artificial clouds or fog using lasers. By ionizing particles in the atmosphere, lasers could induce condensation, forming clouds that could be used for various purposes. In a military context, artificial clouds could provide cover for operations, obscuring the view of enemy satellites or reconnaissance systems. For civilian use, this technology could help mitigate droughts by inducing rainfall in arid regions, offering a potential solution to water scarcity. However, the idea of manipulating weather patterns with lasers is not without its challenges and ethical concerns. Altering natural weather systems could have unintended consequences, such as disrupting ecosystems or creating imbalances in regional climates. There's also the question of who controls this technology and how it's used. Could it become a tool for geopolitical leverage, with nations using weather control to gain an advantage over others? These are complex issues that would need to be addressed as the technology develops. Despite the controversies, the potential applications of space-based laser weather control are undeniably intriguing. From protecting communities from natural disasters to supporting agricultural needs, this technology could have far-reaching impacts on both defense and civilian life. As research progresses, it will be essential to balance innovation with responsibility, ensuring that any advancements in this field are used for the greater good. Next, we'll delve into how space-based lasers could influence international relations and diplomacy. Could the presence of these systems deter conflicts, or might they escalate tensions? Join us as we explore the intersection of technology and global politics. Now, let's turn our attention to a fascinating intersection of technology and global politics: space-based laser diplomacy. The mere presence of these advanced systems in orbit could reshape how nations interact, creating a delicate balance between defense and provocation. Imagine a world where space-based lasers serve not just as tools of protection, but also as instruments of deterrence, influencing the dynamics of international relations. One of the most compelling aspects of this theory is the concept of deterrence. By deploying space-based lasers, a nation could signal its technological prowess and military readiness, potentially discouraging adversaries from engaging in hostile actions. The idea is simple yet powerful. The knowledge that a country possesses the capability to neutralize threats from space could make aggressors think twice before escalating conflicts. This form of deterrence could extend to protecting not only a nation's own assets but also its allies, fostering stronger international partnerships. However, the introduction of space-based lasers into the geopolitical arena also raises significant concerns. While these systems could deter aggression, they might also provoke suspicion and mistrust among other nations. The fear of a technological arms race in space could lead to heightened tensions, with countries rushing to develop their own laser systems to avoid being left at a disadvantage. This scenario underscores the importance of transparency and international cooperation in managing the deployment of such technologies. Without clear agreements and communication, the presence of space-based lasers could inadvertently escalate conflicts rather than prevent them. Another layer to consider is the role of space-based lasers in crisis management. In situations where tensions are high, these systems could provide a non-lethal means of de-escalation. For example, lasers could be used to disable threatening satellites or missiles without causing physical harm, offering a way to neutralize threats while minimizing collateral damage. This capability could serve as a diplomatic tool, allowing nations to respond to provocations in a measured and controlled manner, potentially reducing the risk of full-scale conflict. Yet, the ethical and strategic implications of using space-based lasers in diplomacy cannot be ignored. The line between defense and provocation is often thin, and the misuse of such technology could have far-reaching consequences. It's crucial for nations to establish clear guidelines and frameworks to ensure that space-based lasers are used responsibly, with a focus on maintaining global stability rather than pursuing unilateral advantages. As we look to the future, the role of space-based lasers in diplomacy will likely depend on how nations choose to approach this technology. Will it become a force for peace, deterring conflicts and fostering cooperation? Or will it spark a new era of competition and mistrust in space? These are questions that will shape the trajectory of international relations in the decades to come. Next, we'll dive into the critical role of research and development in advancing space-based laser technology. How are governments, private companies, and academic institutions working together to push the boundaries of what's possible? Stay with us as we explore the cutting-edge innovations driving this field forward. Now, shifting our focus to the backbone of innovation, let's explore the critical role of research and development in advancing space-based laser technology. Without the tireless efforts of scientists, engineers, and visionaries, the theories we've discussed would remain just that, theories. It's the ongoing research and development that transforms these ideas into tangible technologies, pushing the boundaries of what's possible in space defense. One of the most exciting aspects of this field is the collaborative nature of the work being done. Governments, private companies, and academic institutions are joining forces to tackle the complex challenges of space-based lasers. For instance, national space agencies are partnering with universities to conduct groundbreaking experiments, while private aerospace companies are investing heavily in developing cutting-edge laser systems. This synergy between different sectors is accelerating progress, bringing us closer to a future where space-based lasers are a reality. Take, for example, the role of academic research. Universities around the world are conducting studies on laser propulsion, energy efficiency, and materials science, all of which are essential for creating effective space-based laser systems. These institutions often serve as incubators for new ideas, providing the theoretical foundation that guides practical applications. At the same time, government-funded programs are focusing on large-scale testing and deployment, ensuring that these technologies meet the rigorous demands of space environments. Private companies, on the other hand, are driving innovation through competition and investment. Firms specializing in aerospace and defense are developing advanced laser prototypes, often leveraging breakthroughs from academic research. These companies are not only contributing to technological advancements, but also shaping the economic landscape of space-based defense. Their involvement ensures that the development of space-based lasers is not just a scientific endeavor, but also a commercially viable one. However, the path to success is not without its challenges. Developing space-based lasers requires overcoming significant technical hurdles, such as creating lasers powerful enough to be effective in space while ensuring they are energy efficient and durable. Additionally, the integration of these systems with existing satellite networks and defense infrastructures poses its own set of complexities. This is where collaboration becomes indispensable. By pooling resources and expertise, governments, companies, and academic institutions can address these challenges more effectively, paving the way for breakthroughs that might otherwise be unattainable. Looking ahead, the importance of research and development cannot be overstated. As we continue to explore the potential of space-based lasers, it's clear that the progress we make today will shape the future of space defense. The collaborations between governments, private companies, and academic institutions are not just advancing technology, they are laying the groundwork for a safer, more secure world. Next, we'll delve into the ethical considerations surrounding space-based lasers. How do we ensure that these powerful technologies are used responsibly? Join us as we examine the moral and philosophical questions that come with harnessing such advanced capabilities. Now, as we turn our attention to the ethical dimensions of space-based lasers, it's important to consider the profound implications of deploying such powerful technologies. While the potential benefits are immense, so too are the risks, particularly when it comes to the weaponization and misuse of these systems. The ethical questions surrounding space-based lasers are not just technical or scientific. They are deeply rooted in how we, as a global society, choose to wield this newfound power. One of the most pressing concerns is the risk of weaponizing space-based lasers. While these systems hold promise for defense and protection, they could also be repurposed as offensive weapons, capable of targeting satellites, spacecraft, or even terrestrial assets. This raises significant moral questions about the militarization of space. Should we allow weapons to be stationed in orbit, potentially escalating conflicts and destabilizing international relations? The idea of space becoming a new battlefield is a sobering one, and it forces us to confront the ethical boundaries of technological advancement. Another critical issue is the potential for misuse. Space-based lasers, if not properly regulated, could fall into the wrong hands, whether through state-sponsored aggression or unauthorized access by rogue actors. The consequences of such scenarios could be catastrophic, disrupting global communication networks, crippling navigation systems, or even causing physical harm. This underscores the need for robust international oversight and accountability, mechanisms to prevent abuse and ensure that these technologies are used responsibly. To address these challenges, international treaties and regulations play a vital role. Agreements like the Outer Space Treaty of 1967, which prohibits the placement of weapons of mass destruction in space, provide a foundational framework for governing space activities. However, as technology evolves, so too must our legal and ethical frameworks. New treaties and regulations will need to be developed to specifically address the unique challenges posed by space-based lasers, ensuring that their deployment aligns with global security and ethical standards. Moreover, the ethical considerations extend beyond just preventing harm. They also involve questions of equity and access. Who gets to control these technologies, and how do we ensure that their benefits are shared fairly across nations? The risk of creating a technological divide where only a few powerful nations possess the capability to deploy space-based lasers could exacerbate existing inequalities and tensions. This highlights the importance of fostering international cooperation and inclusivity in the development and governance of these systems. Ultimately, the ethical deployment of space-based lasers requires a delicate balance between innovation and responsibility. As we continue to push the boundaries of what's possible, we must also remain vigilant in safeguarding against the risks and ensuring that these technologies serve the greater good. The decisions we make today will shape not only the future of space defense, but also the moral legacy we leave for generations to come. Next, we'll explore the economic implications of space-based lasers, examining the costs, funding sources, and potential return on investment. How do we balance the financial demands of such advanced technologies with their strategic value? Stay tuned as we dive into the economics of space-based defense. Shifting our focus to the financial side of things, let's explore the economic implications of space-based laser systems. Developing and deploying these advanced technologies is no small feat, and the costs involved are staggering. From research and development to manufacturing, launch, and maintenance, the financial demands are immense. But with great expense comes the potential for significant returns, both in terms of strategic value and long-term benefits. The initial costs of developing space-based lasers are substantial. Research and development alone require billions of dollars as scientists and engineers work to perfect the technology. Manufacturing the lasers, along with the satellites or platforms that carry them, adds another layer of expense. And then there's the cost of launching these systems into space, which can run into the hundreds of millions of dollars per mission. Once in orbit, ongoing maintenance and upgrades further contribute to the financial burden. These costs are not just one-time expenses, they represent a continuous investment over the lifespan of the technology. Funding for such ambitious projects typically comes from a mix of government budgets, private sector investments, and international collaborations. Governments, particularly those with advanced space programs, often take the lead in funding these initiatives due to their strategic importance. However, private companies are increasingly playing a role, driven by the potential for commercial applications and partnerships with public entities. International collaborations can also help distribute the financial burden, allowing multiple nations to pool resources and share the benefits. But what about the return on investment? While the upfront costs are high, the potential benefits could justify the expense. Space-based lasers could revolutionize defense systems, providing unparalleled capabilities for missile interception, satellite protection, and planetary defense. These systems could also have civilian applications such as space debris cleanup or energy transmission, opening up new revenue streams. Additionally, the technological advancements made during development could have spillover effects, driving innovation in other industries and creating economic opportunities beyond space defense. Balancing these costs and benefits is a complex challenge. Policymakers and investors must weigh the immediate financial demands against the long-term strategic and economic advantages. The key lies in careful planning, transparent budgeting, and a clear vision for how these technologies will be used to benefit society as a whole. As we consider the economics of space-based lasers, it's clear that the financial stakes are as high as the technological ones. The decisions we make today will shape not only the future of space defense, but also the economic landscape of tomorrow. Next, we'll examine the environmental impact of these systems, exploring how they might affect Earth's atmosphere and the broader space ecosystem. Stay tuned as we delve into the sustainability challenges of space-based lasers. Now, let's turn our attention to the environmental implications of space-based lasers. While these systems hold immense potential for defense and technological advancement, it's crucial to consider how they might affect both Earth's atmosphere and the delicate balance of space ecosystems. After all, sustainability is a key factor in ensuring that our advancements don't come at the cost of our planet or the broader environment. One of the primary concerns is the potential impact of laser beams on Earth's atmosphere. High-powered lasers, when directed toward Earth, could interact with atmospheric layers in ways that are not yet fully understood. For instance, the intense energy from these beams might cause localized heating or ionization, potentially disrupting communication signals or even affecting weather patterns. While these effects are likely to be minimal, they highlight the need for careful regulation and monitoring to prevent unintended consequences. Beyond Earth, the deployment of space-based lasers raises questions about their impact on the space environment. Space is far from empty. It's home to satellites, space stations, and even natural phenomena like micrometeoroids. The use of lasers in space could contribute to the growing problem of space debris if not managed properly. For example, vaporizing debris with lasers might seem like a solution, but the process could create smaller fragments that remain in orbit, posing new risks to spacecraft and satellites. This underscores the importance of developing sustainable practices for space operations. Another consideration is the energy required to power these lasers. Generating the immense energy needed for space-based systems often relies on non-renewable resources or nuclear power, both of which have their own environmental trade-offs. As we move forward, it's essential to explore cleaner energy sources such as solar power to minimize the carbon footprint of these technologies. Balancing the need for powerful defense systems with the imperative to protect our environment will be a critical challenge in the years to come. Sustainability also extends to the materials used in constructing space-based lasers. Many of the components required for these systems are rare or difficult to produce, raising concerns about resource depletion and environmental degradation during extraction and manufacturing. Developing more efficient and eco-friendly production methods will be key to ensuring that these technologies can be deployed responsibly. As we consider the environmental impact of space-based lasers, it's clear that sustainability must be at the forefront of their development and deployment. By addressing these concerns now, we can create systems that not only enhance our defense capabilities, but also protect the planet and the space environment for future generations. Next, we'll envision a future where space-based lasers are a common part of our defense infrastructure, exploring how this technology could shape global security and daily life. Stay tuned as we dive into the possibilities of tomorrow. Now, let's step into the realm of possibility and imagine a future where space-based lasers are not just experimental concepts but integral components of our global defense infrastructure. Picture a world where these advanced systems are as commonplace as satellites, quietly orbiting above us, ready to respond to threats with precision and speed. This future isn't just about technology, it's about how it reshapes the way we think about security, diplomacy, and even our daily lives. In this envisioned future, space-based lasers could serve as a first line of defense against a wide range of threats, from incoming missiles to rogue asteroids. Their ability to neutralize dangers before they reach Earth would fundamentally alter the landscape of global security. Nations might rely less on ground-based missile systems, shifting their focus to space-based solutions that offer broader coverage and faster response times. This could lead to a new era of deterrence, where the mere presence of these lasers discourages potential adversaries from hostile actions, but the impact wouldn't stop at defense. Space-based lasers could also play a transformative role in everyday life. Imagine a world where these systems are used to protect critical infrastructure, such as power grids and communication networks, from cyber attacks or physical sabotage. By safeguarding these systems, space-based lasers could ensure uninterrupted access to essential services, enhancing our quality of life and economic stability. On a larger scale, the deployment of space-based lasers could influence international relations. Countries with advanced laser technology might gain a strategic edge, leading to new alliances and partnerships. At the same time, the potential for misuse could spark debates about regulation and oversight, prompting global cooperation to establish guidelines for responsible use. This balance between innovation and accountability would shape the geopolitical landscape, fostering both competition and collaboration. For the average person, the presence of space-based lasers might not always be visible, but their effects would be felt in subtle yet significant ways. From more secure global communications to enhanced disaster response capabilities, these systems could create a safer, more connected world. They might even inspire new industries and job opportunities, driving economic growth and technological advancement. As we look ahead, it's clear that space-based lasers have the potential to redefine not just defense but the very fabric of our society. By integrating these systems into our future, we can envision a world where technology and humanity work hand in hand to overcome challenges and unlock new possibilities. Next, we'll explore the challenges that stand in the way of making this vision a reality, examining the technical, political, and logistical hurdles that must be addressed. Stay with us as we delve into the final piece of this fascinating puzzle. Now, as we turn our attention to the final piece of this puzzle, it's time to address the challenges that stand between us and the widespread adoption of space-based laser systems. While the potential is immense, the road to making this technology a reality is paved with significant hurdles, both technical and otherwise. Let's break down these challenges and explore how they might be overcome. First, the technical challenges. Space-based lasers require cutting-edge technology, from powerful energy sources to precise targeting systems. One of the biggest obstacles is developing lasers that are both powerful enough to neutralize threats and efficient enough to operate in the harsh environment of space. Current energy storage and generation systems may not yet be sufficient to support continuous operation, especially for large-scale defense networks. Additionally, maintaining and repairing these systems in orbit presents its own set of difficulties, as sending repair missions into space is costly and complex. Then there's the issue of political and regulatory challenges. The deployment of space-based lasers raises questions about sovereignty, international law, and the militarization of space. Who gets to control these systems, and how do we ensure they're used responsibly? The potential for misuse or accidental escalation could lead to tensions between nations, making it essential to establish clear guidelines and treaties. Global cooperation will be key to navigating these complexities, but achieving consensus among competing interests won't be easy. Logistical challenges also loom large. Building, launching, and maintaining space-based laser systems requires significant financial investment and infrastructure. The cost of developing and deploying these systems could run into the billions, and securing funding from governments or private entities may prove difficult. Furthermore, coordinating the logistics of launching and operating these systems on a global scale would require unprecedented levels of international collaboration and resource sharing. Despite these challenges, solutions are on the horizon. Advances in energy storage, such as next-generation batteries or space-based solar power, could provide the necessary power for laser systems. Innovations in autonomous robotics might enable self-repairing satellites, reducing the need for costly maintenance missions. On the political front, international organizations could play a role in creating frameworks for the responsible use of space-based lasers, fostering trust and cooperation among nations. As for the timeline, it's difficult to predict exactly when these challenges will be fully overcome. Some experts estimate that we could see functional space-based laser systems within the next 2 to 3 decades, provided there's sustained investment and collaboration. However, the pace of progress will depend on how quickly we can address the technical, political, and logistical barriers. In the end, the journey towards space-based laser defense is as much about innovation as it is about collaboration. By tackling these challenges head-on, we can unlock a future where space-based lasers not only protect our planet, but also pave the way for new possibilities in technology and global security. And with that, we've reached the end of our exploration into the 25 theories on how space-based lasers could revolutionize defense. Thank you for joining us on this journey. Don't forget to share your thoughts in the comments and subscribe for more insights into the future of technology and beyond. As we bring this exploration to a close, let's take a moment to reflect on the incredible possibilities we've uncovered. From asteroid defense and satellite protection to space-based power beaming and planetary colonization, the 25 theories we've discussed paint a vivid picture of how space-based lasers could transform not only defense but also the way we live and explore the cosmos. These technologies have the potential to safeguard our planet, enhance global security, and even pave the way for humanity's expansion into the stars. But as we've seen, the journey to realizing these possibilities is not without its challenges. Technical hurdles, political complexities, and logistical demands all stand in the way. Yet, with innovation, collaboration, and a shared vision for the future, these obstacles are not insurmountable. The question now is not if space-based lasers will become a reality, but when and how they will shape the world we live in. So, what do you think? Will space-based lasers become the cornerstone of future defense systems? Or will they open up entirely new frontiers for exploration and discovery? The future is waiting to be written, and your voice is part of that story. Share your thoughts in the comments below. Do you see space-based lasers as a game changer, or do you have concerns about their implications? If you've enjoyed this deep dive into the future of technology, don't forget to hit that like button, subscribe to the channel, and ring the notification bell so you never miss out on the latest insight. Together, let's keep exploring the possibilities of tomorrow. Thanks for watching, and until next time, stay curious.